In this recording, we're going to work out with one example of multicollinearity. Okay, so in our earlier recording, what we have done was that we have introduced what exactly multicollinearity is. The two independent variables, they are correlated with one another. You cannot separate out the effects of one variable from the other variable on the dependent variable. And in case if you try to omit any of these variables, then the results could be significantly altered. Okay, now let us see this example. In this example, say there are three models A, B, and C. In the first model, you have two independent variables x2 and x3. In the next model, you have again other two independent variables x2 and x4. And in the third model, you have all the three variables x2, x3, and x4. Okay, that is in the C model. So, and of course these parameters are going to be different when you run the regression. Okay, the constant value, the slope parameters, they'll be different. Okay, in case if you are picking up different variables, okay, in all of these models, and that's the reason I have put up beta 1, alpha, and gamma, and so on. So, and also further assume that the correlation between x2 and x3 is 0.97, correlation between x2 and x4 is 0.82, and correlation between x3 and x4 is 0.99. Quite heavy correlation among all of these variables. So we have taken the pairwise correlation of each of these variables. Now the point is, let us look at this example here. So here there are three models A, B, and C. This is constant x2, x3, x4. Clear? And you have the r bar square here. In the first model, you have just x2 and x3, as you could see here. In the second model, you have just x2 and x4, as you could see above. And in the third model, you have all the three variables x2, x3, and x4. The numbers which are written in white, they are the coefficient numbers, and the number which are written in the parentheses, they are the standard errors. Okay. So supposedly, if say x2 is the most important variable, say for example, x2 is the most important variable, you just can't let out with this variable. You just can't ignore this variable. And that's the reason x2 is lying in all the three models. You can probably play with x3 and x4, but you can't play with x2. x2 is the most important variable. You cannot ignore it. Now, but x3 and x4 are also important. Notice that the correlation between x3 and x4, the correlation between x3 and x4, this is quite huge. Okay, almost perfectly correlated. This is quite huge. Now look at model C. When both of these variables, they are included in the model x2, x3, and x4. This is model C. Now what happens to their statistical significance, x3 and x4? 0.82, 0.69. This is low statistical significance. This is low statistical significance. They are individually, they have very low statistical significance. But when they, and now just look at, when you drop one of these variables in either model A or B, then now look at the statistical significance of these variables. This is high. This is high statistical significance. So rule of thumb is, in case if the t statistic, I'm so sorry, I mean these parenthesis values not standard errors, these are t statistics. I'm so sorry. Yeah, so when you have dropped these variables from the C model, say in model A you have dropped x4, and only what is left is x3. So now compare the statistical significance of x3 in model A to x3 in model C. It has turned from a low significance to high significance. Similar is with the case of x4. Compare the statistical significance in model C of x4, which is low statistically significant, to model B of x4, this is high statistical significance. So their statistical significance has increased. Now, in case if you look at, though I haven't given you this, but supposedly, supposedly, I have not given you that, but I'm sure that this is going to be the case, that F statistic, in case if you compare, supposedly, in case if you compare the F statistics of all of these three models, then F statistic in model C is high and significant. Now let me ask you a question. What do you think F statistic tells you? F statistic tells you whether all the variables which you have included in the model, are they jointly significant? Okay, so in model C, you have included all the variables x2, x3 and x4. The question is that F statistic is trying to tell you, are all these are all these variables jointly significant? Point is that they are not individually significant. Individually, in case if they are, if you look at them, they have very low significance. But if you jointly look at them, their significance is quite high, which will be given by F statistic. Okay, and I'm telling you that in model C, it is highly significant. So this is a kind of contradiction. Low individual significance, but high joint significance. So, and even if you look at the coefficients of x3, x4, fine, you will find this along each of these models. You'll find them that they are quite different. Okay, minus 12 to 42.41, 3.82 to 2.1, and so on. So they are also being affected. So when you're dropping one of these variables, the results are getting altered. So this was the meaning of results getting altered. You're moving from low significance to high significance, your coefficients getting altered, your F statistic is very significant, but your T statistics are very low and insignificant. So these are all pointing towards the problem of multicollinearity. So how do you detect multicollinearity in the model? Let me just point out for you guys. One, there is high correlation among independent variables. There is low T statistics, high and significant F statistic, and significant changes in coefficient of variables across models. So this is the way you will detect the problem of multicollinearity. I hope this would have helped you. Thanks.